Hello, this is David D. Hilster. I am your critical thinker, dissident scientist, and I'm here to tell you the truth about science, something you university professors won't tell you, the mass media won't tell you, and certainly those science evangelists, they'll never tell you. But I'm here with one of my favorite scientists of all time, and I think he's going to go down in history. He's one of the great scientists of our generation. Of course, in our generation, not many people always know that, but that's my job, is to get everybody to know these people. And I'm talking with Glenn Borchardt, who's going to be the infinity guru. Well, welcome, Dr. Glenn Borchardt, right?
No, thank you so much. Wonderful introduction.
I know he's so,
A little much,
so.
but anyway.
Well, I've known you for quite a while. It was one of those aha moments. I've only had about 3 aha moments in when hanging out with you great scientists. Well, one was in 2008 when I saw Lionel Deneu's underwater experiments. I thought that was quite shocking. It blew my mind. The other one was when I read the universal cycle theory with you and Steve Pwetz. Is it Pwetz? How do you pronounce that?
He called himself Pitts.
Pitts. Okay.
Yeah,
That's
right.
what we
Like
like
gravel
about.
pit. Yeah, he likes that.
That's cool. It's easier than whatever it may sound like. But Steve Pitts
I
and
I I, I think it's putts really, but it's
yeah. There's no correlation between our orthographic, which is the spelling system, and our pronunciation in English. We don't have an academy of letters like they do in Portuguese and French. We decided we want to just not update our orthographic system. So Pitts. But anyways, that blew my mind. Really, mostly what blew my mind was the neo-mechanics and the infinity, where you had, ether 1, ether 2, ether 3, and I mean, that exploded my brain. I remember that day quite clearly. And
well,
then,
that's great.
so we have you here today because you have a new book out. I'll put that on the screen here, and the title is called Infinite Universe Theory. Can you tell us a little bit about this particular book? Because I've talked about some of your other books already.
I've been pushing infinite universe for quite some time, actually, in all my other books. As soon as I use the infinity assumption, which says that universe is microcosmically and macrocosmically infinite. And this title, I love it. There's no subtitle, you'll know. It's just Infinite Universe Theory. This is the book. This is the book that kind of puts it all together. And I'm really proud of it. It's taken me about 10 years to get it all together. And what I try to do, as we did in universal cycle theory, is try to avoid any kind of contradictions whatsoever. And as you know, in the Big Bang Theory and relativity, there are contradictions galore. And so that was what the whole point of it was. And of course, you can read the blurb on it if you go to Amazon, put in Infinite Universe Theory, you will come up with that book first thing, and you'll see that the pitch is there about it. And I don't give a whole lot of details in that pitch, but you can get some idea just by going to look inside the book at Amazon, and price is only $9.99. So I try to keep it as cheap as possible so that more people around the world can read it.
No, absolutely. And I downloaded. In fact, I remember when you told me, I knew about it, and it was like, okay, I'm going to go download it. So December 25th, I had to wait. So I was pretty upset with you, but that's okay. On on Christmas Day, I actually got it and I downloaded it and I just started flying through it. Of course, one of the good things about it is you also put down a lot of the foundation that you have been developing, like the 10 assumptions of science, correct?
Yeah, that's right. And what we're talking about is a major paradigm shift. Actually, if you will, it's the biggest paradigm shift we can ever have, because we're going from a Big Bang theory that exploded out of nothing to infinite universe theory, which says that the universe always existed and existed everywhere. There's no place for anything else. And so that's that's really a big thing. So, in order to do that, of course, you have to change fundamental assumptions. That the reason the current Big Bang is so popular and Einstein's so popular, is they're using the wrong assumptions. And so, because of that, I started out long ago. I think I wrote a book in '04, and actually in '84, I had a lot of these assumptions all together. And one of the things that they have, there's a couple requirements for the assumptions, and this is what I learned from Collingwood. in 1940, he said, well, you have to, if you're going to have fundamental assumptions, they have to be opposites. In other words, you have finity and infinity. Second thing is you cannot prove them without a doubt. You can support them one way or the other, but you can't prove them. And the other thing is, if you're going to have more than one assumption, they have to be con-supponable. What that means is that you're supposing assumptions. These are not provable, remember. But if you do have more than one, they have to be con-supponable. Con means with supposition. It means that if you assume number one, then number two can't contradict it. And that's essentially what we've done here with the 10 assumptions. Now, you could have an infinite number of assumptions, I suppose, too. But, and you could only have one if you want. But this helps to explain a lot of what we do in science. And I think 10 for pedagogical reasons and historical reasons was a good number. And I couldn't really think of the 11th one. So that's probably why I'm at 10.
Yeah, I don't know. Maybe it's built into us because of our 10 fingers and digits in our math system. I went through the book when I read through it, and I made some notes. On Kindle, you can make some highlight some stuff. So I'm going to go through those. Again, I will have a link for everybody to take a look at this. Before I do, though, I mean, I think what's really what you were saying about this is a huge paradigm shift is that it's really amazing I think that most people really have this feeling that the universe has always been there. And well, if you have a Big Bang, it's happening somewhere, and there was something before that, even if you were to believe in the Big Bang. But this idea that you have infinite down, it goes against a lot of things in physics, which is like the idea of looking for the God particle or the ultimate particle, because you're not going to find one. There's always going to be stuff down there. But the idea of infinite levels in the universe is something extremely important. And I know it's important to my father and I's theory. I mean, we have literally, yours is an ether theory, for instance. Ours is a particle theory, but we use your infinite, I mean, it is completely based on your stuff. We have G1 particles and G2 particles and G3 particles, and our waves of particles are the light, what is light. And so it was really funny that my father, before we get into this, I'm just telling you a story with my father. I was always talking about you, and I said, you got to read Glenn Borchardt, you got to know this infinite stuff. And he was working on his stuff, but it was really funny because I said, well, you know, Dad, if you've got G1, you got G1 particle. And the other blowing of my mind happened to be when he, in July of 2015, solved one of the solutions you can have for the wave-particle duality. And I was just, my mind was blown, but I was kept talking about, well, you know, if there's G1, there's G2, there's particles all the way down. And he just, I don't want to know about it. And I remember probably about a year later, maybe, he'd come over and we're hacking the universe with this model. I think it's a very viable model, different from the ether model, but it's, again, totally based on infinity. He came up to me and says, well, you know, G2, and I just stopped him. Before he even said anything, what? Now you're talking about another level? Well, you have to have it. He says, if there's motion in the universe and G1, which is light and gravity in our model, and that curves, well, guess what? There's something below it that has to make a curve. And I said, I've been telling you this. Well, I didn't invent it. It came from your work. And it was just so funny that in his engineering mind and in our Newtonian world where, you know, he doesn't have all this magic stuff. We don't have charge. We don't have all this stuff. This stuff is, it's mass and exact. I mean, it follows your stuff right to the tail. That he didn't believe what I said, didn't believe what you said, but when he got to the point where he needed it and it was necessary, he goes, oh, there it is. And now he's doing G3. So it was really amazing to see somebody who really embraced this idea, because you know, it's really it comes down to the micro and macro cosms that you talk about, where, you know, everything that's at this level, there's something else below it. So if it's moving and it's curving, something, you know, something's making that happen, and it's in a level below and a level below. But I just wanted to put that spiel out there, give my subscribers a little bit of context here. I'm going to get to this first highlight here at location 328, right in the beginning. Here's what, you don't have to see it, I'll just read it to you. You say, being skeptical and commonsensical by nature, I investigated modern physics systematically from top to bottom. What I found was shocking. The whole thing was an enormous stinking can of dead worms. Now, I couldn't resist that. Now, obviously, that is a very strong statement, and that was in the beginning of your work, and I think it's a good way to start. You know, how did a geologist who is a very successful geologist, your doctorate degree is not neither in philosophy nor in physics, correct?
Well, it's actually in soil science, so it's even more fundamental because we have our feet on the ground, right? That's the point. And
so what did
all
you mean
this,
by this whole thing as enormous thing? You obviously looked at it. This is a statement saying, I looked at current science and I found this. Take us to that place.
okay, let me explain a little bit what we do in science is we look for various bits of data, right, and information to now, especially in soils and in geology, what you do is you find a rock or soil and then you study it and then you look at its position in relation to others and then you put the whole story together and it can't contradict. You know, in other words, it's consupponable, if you will. And so that's what I've been doing my whole life. And when I looked at physics and cosmogony, and I call it cosmogony because cosmogony means the study of the origin of the universe. Mm-hmm. Of course, you assume that the universe had an origin with that. Anyway, I looked at that, and boy, it was a mess. And there were contradictions all over the way. Wave particle duality, this, that, and the other thing, 4 dimensions, time as matter, all that is just a mess. And that's kind of why I used the colorful language I did, so that people could get the point that it's not so good right now. Physics is really in bad shape.
Yeah, I mean, it truly is, and I think one of the amazing things is that we find, especially with the internet today, we keep finding people who have come to the same conclusions. I think it really basically comes down to you giving you. I always have given my ability. My father's the same way. We always give ourselves the complete ability with an open mind to see anything. The more bizarre it is, actually, I will be attracted to it to take a look at it. But you know what's really sad is some of the most bizarre stuff I read about is from mainstream physics. So you know, yeah, right. It's really amazing. I'm going to go to a next quote here, or highlight I made. It says, in the popular press, this is, make sure, yeah, in the popular press, there's a great fuss about the search for the grand unification of the 4 forces, which are considered as if they were actual things of the results of things hitting things. Can you explain that a little bit?
Okay, I talk a lot about matter-motion terms being used in physics, and those are terms in which you multiply a term for matter times a term for motion. So, example, a momentum is P equals mv. So it's mass times velocity, and you get motion. I get a momentum. Momentum doesn't exist, though. And force is the same way. Force equals ma, mass times acceleration. It's a calculation. Mm-hmm. And so the forces don't exist. Mm-hmm. Energy doesn't exist. Momentum doesn't exist. Right. What exists is the matter. Okay, that's what exists. And so these are just calculations. They're wonderful. They help us understand matter and motion. But you need to know in an F equals ma equation, you need to know what is colliding with what. That's the key thing, and that's where I essentially had stripped this down to. It's always matter in motion, motion of matter. That's all that the universe is about.
Yeah, that is something, and again, in our model is the same thing. In fact, the title of our book, I believe, it's somewhere around here, it just says the entire universe as mass in matter in motion. And you know, all those equations, all of those things that we write down are useful, but it's really hard. It seems like, you know, you were talking about the cow eyes or the deer in the headlights sort of look when you talk about all this stuff. One of the things is that when you tell people, really all you have in the universe is matter and it's moving, and it'll collide, that'll happen, but it seems to really make their eyes glaze over. They can't. It seems like math is so part of the of this whole system. I'm going to go to the next one here. Here's another a note I took at location 1645. This is Kindle. This is the new age of books and stuff. It says, note that the cosmogonists even disagree on whether the laws of physics existed before the Big Bang. Hawking, for one, writes, because there is a law such as gravity, the universe can and will create itself from nothing, conveniently forgetting about conservation. So you talk a lot about the Big Bang, and do you feel that when I read that, what you're saying, you're formalizing what I think a lot of people see? I have an intuition for that. I don't consider myself a physicist born out of the womb, and I'm a physics person. But my curiosity in science, it just seems like this idea that it was something created from nothing. I don't think the average person really believes that. Yet here we are having to discuss this.
Yeah, and here we are, year 2018, and still talking about such. And of course, when I listened to one of Hawking's talks, when I introduced the scientific worldview, in fact, I was hoping to ask him that question, that how does this Big Bang fit with conservation? And of course, they call it conservation of energy, but I call it the conservation of matter and motion.
Sure.
And he wouldn't have an answer for that. That's a total rejection of the conservation law, which is the first law of thermodynamics. Yeah, I've used it all the time in my work. I don't find any reason to not. And here is this Big Bang coming along saying, "Oh, pop out of nothing."
Yeah, absolutely. I think one of the things I've noted throughout your work throughout the years is you're really looking at the Big Bang. Was that one of the first things you really looked at when you were starting all this work? It seems to be really integral. You use it as an example, but oftentimes those examples come from our own investigation. Was that something you investigated early on, or?
Yes, indeed. In fact, in 1977, I was still a Big Banger, and if you'll read my preface,
no,
the first part,
I can't believe this.
And the point is, well, this is 1978. This is a long time ago.
Oh, okay, all right, yeah.
And I thought, wow, they've discovered how it all started. Wow, isn't that really great? And then, of course, I got into checking it out, and then it didn't make any sense, and it conflicted with many other things, like, for example, conservation. So, and the other thing about infinity is that you always get involved in infinity. Even if you say that the universe exploded out of nothing, you always have to say, well, then where did that come? And Hawking was asking that question. I remember in his talk, I didn't learn anything except for one thing. He said, Woody Allen had this great quote. He said, infinity is a very long time, especially near the end. And that was Woody Allen. I thought that was really great. So even if you think there's a God that invented the universe, then you have to say, well, who invented that God and that God, next God? You're always involved in infinity. You can't.
Nope, we're glitching here a little bit.
So why not? But the universe end anywhere? Why would the universe end anywhere?
Sure.
Could be dragons there all of a sudden? Not possible. Just goes on and on.
Yeah, no, absolutely. In fact, I heard something on the radio, I think yesterday or the day before, maybe yesterday, on AI, and they were talking about, well, if there's, something that's this big machine that made us, like we're some high school project of some advanced being, right? Well, then they said, well, then of course, then we have the reason why. We've answered the why. But then even the person on the radio, these things are starting to come. That's why I'm thinking that your work and other people's work is really going to come of age, because people they weren't saying that 30 years ago. You didn't hear them say that those kinds of things. And he said, well, then you have to explain the high school being that's making us, and then you have to explain who it's made them, et cetera, et cetera. So so it seems to be going on and on. So okay, let's keep moving ahead, because I did take my notes here. I'm trying to hit on some things here that are more You know, because you and I can talk about stuff, and if you have been around Glenn and if you read his work, we always, no matter where we are, we can talk and talk and talk, and it can be very almost seemingly esoteric. So I'm trying to pick on some things here, Glenn. I apologize, that are more mainstreamy kind of things here, and leave the readers to be able to talk, read your books in full. Here's another one quote I have from location 2122. In this regard, the E equals mc squared equation has been widely misinterpreted as representing the conservation of mass into energy, and the belief that mass and energy are the same thing. This is not possible because energy neither exists nor occurs. So tell me about that. About
right. Yeah. Okay. Remember that energy is an equation. One example is E equals 1 mc squared, and the question is, what happens in the case of E equals mc squared? Essentially, it is a description of the absorption of motion internally in a microcosm, which I call a portion of the universe, and then the other part of it is the emission of motion. Now, in the case of Einstein, with his denial of ether, this emission could not occur other than as some magical energy thing. We don't know what it was. What really happens is that every microcosm, every portion of the universe is surrounded by ether, and these ether particles absorb the motion. And this produces a wave that takes off as EM, electromagnetic magnetism, and is light, essentially. Microcosms operate, and so that's why some people, some of the dissidents don't like E equals mc squared, and probably the reason is they don't like this magical energy thing. And I'm saying, hey, it's not leading that way. It's leading through motion counteracting the boundary of the microcosm and contacting ether particles that surround every single thing in the universe.
Yeah, I mean, it does come from stuff that we've been studying with electromagnetic waves. And so if you have a physical model, then and an equation seems to, it's hard to verify, I think, in some sense. But there is an explanation. What you're saying, and what we talk about equals mc squared a little bit, I think, in our book, is that you are translating that equation, which is E equals mc squared, into matter and motion, and the motion matter, right? That's what you're doing. So
right.
And
what you're doing is just look at it this way. You can pick any portion of the universe, and you're going to have all the laws that Newton came up with. The first law, object keeps going until it hits something. The second law, one thing collides with another, and the third law, the reversal. So that's what we're talking about. So all you're talking about is the changes in kind of motion. You're taking the internal motion and you're converted into external motion. That's all you're doing. That's no big brainer. And if you take out the boundary and the fact that that you have a microcosm there, it's just the same as Newton's 3 laws. No difference.
Yeah.
But you do have to have one thing, and that is you have to have ether or something.
Right.
You have to have something outside of whatever it is that you're studying.
Right. No, absolutely. In fact, when I was reading your book, I think it's really amazing. This is one of the things. There's this guy called Robert Dissident. If people take a look at my video previous to this, Laura Gardee, who works with fractals and was looking at the patterns that she sees, like in galaxies and stuff. There's some interesting things there. She found this guy. And he is like this electrical engineer. It seems like electrical engineers are really feet on the ground people. I mean, they get this stuff right away. It seems like I think it's because they work with real circuits all the time, with real physics all the time, and they measure it, they look at it, they have their equations for it. But they see, and this guy talked about, he called polytheism. Now, I had not seen that word before, but basically it means more than one theory. Now, if you look at the infinite universe theory, right now it's supporting 2 very good models, very good ones. I mean, my dad and I have a model that isn't ether, but like you said, everything has to be mass and motion, matter and motion, everything. And that's what we're using. There's a lot of similarities. There's pluses and minuses to each one. But what you've given the world in the infinity all the way up, turtles all the way up, and turtles all the way down, it's supporting right now two very good models, in my opinion. We can't break it. Every time we think we found something where we can't hack it with matter and motion, we do. And I think that's one of the things that my dad and I have kept going with it, because what we're really doing is, and he and I think yourself would be included, other people who do subscribe to your work, you really start to understand that all this other stuff like charge, people take these little circles and they put a plus on it, then they put another circle next to it with a minus on it, and they move. And they say charge is a sort of innate thing. And that to me is so foreign. And in your model, seriously, if it wasn't for your work, our physical model wouldn't exist. I don't think we would have come up with it in any shape, way, or form. And the reason we can continue to hack the universe with our particle model is because of the infinite levels. That's why we just don't like the idea that at some point, if you say this is the bottom line, you got to give it magical powers.
Yeah, right. Well, and of course, one of the things I point out is that solid matter is an idealization. Empty space is an idealization.
Sure,
those don't exist. Those are just ideas. Everything is in between, and so that means there's no finite particle. Not possible. And there's no empty space. If there's no empty space, what does that mean? That means non-existence is impossible. The universe can produce a lot of stuff, but one thing it can't produce is empty space.
Yeah, that's one
non-existence.
Yeah, that's one of the things that just blows your mind, because if you start to look, I heard on the radio this one guy was interviewing a mainstream physicist. It got bizarre the further it went in, but I won't even talk about that part. But what's interesting that this interviewer, who was obviously a pretty much a layman, this was not even a real studied scientist person, was talking about how come my finger doesn't go through the desk when I put my finger on top of the desk. Why does it stop? And he says, and then when you started, he even spoke with the mainstream person, you really do get in this problem, because there's all this space, but there's stuff, and so when you get down to it, the atoms are made out of protons or a nucleus and stuff going around it, and so, but what's really touching, and you get to a point where you have to understand part of your model, and the way I explain it is, there's some things that are uncomfortable with it, but the way I tell people is, I am way more comfortable with Borchardt's infinite universe theory than I am with all this other mumbo jumbo of 11 dimensions and parallel universes and brains starting big bangs, the universe the size of a pea. But there are one of the uncomfortable things is it's like everything's wispy. You're never really at the mass, and you're really never at the space. But that seems to be part of inherent to your model, isn't that correct, or theory, right?
Right. And, George Coyne also really emphasized this, that matter is an abstraction.
Yeah.
And I think that is really good. And all we have is examples of matter. It's like fruit. Fruit's an abstraction. And we have examples of fruit, apples, oranges, and so on. But there's no such thing as fruit. And there's no such thing as matter. So that's another reason that nobody's going to ever find a particle that is filled with matter per se. That's not going to ever happen. And so that's really one.
Wait a minute. Are you saying that the Higgs boson isn't real? Because isn't that the one? They found it. Glenn, you're wrong. They found it. They found the particle that gives, what did they say?
That's a real strange one, remember, because it isn't inside of any particles. It's 25 times the size of a proton. So anyway, it's outside of it. So this is like, I was trying to think of an example that it's like the glue, in the outside. And so the ether deniers have now found yet another way of expressing what ether does. So that's what the Higgs is all about. And it's interesting that it only lasts to 10 to the minus 22 seconds. So
Yeah,
if
yeah,
it's giving anything matter, it's disappearing pretty fast.
yeah.
It's what I call it is accelerator bubble. So there goes your tax money trying to find some.
Well, that's one of the
Kind of
things
ridiculous.
yeah, it's one of the things I really love. I'm going to be interviewing him. He wrote this book here for my subscriber. They know the Einstein Lost Keys. He talks about variable speed of light,
Uh-huh.
and but what's amazing is we got Dr. Alexander Unziker, who's a physicist, a doctor in physics, who's German, running around Europe interviewing people from the mainstream and writing books like The Higgs Fake and interviewing these people. So
Sure.
he's quite a brave guy to get out there. I'm going to move on here to some more notes I've picked up. Again, trying to make sure we stay with some things for the audience here, and not just be this totally wonderful conversation you and I can have and just forget the audience, right? So, but here's another one at location
For that.
2674. Here it says, there are no absolute constants in nature. The speed of light is no more constant than the speed of sound. Can you, I'd love to have you
Right.
comment on that.
Right. Well, it depends on where this light is moving. Obviously, if it's moving through water, it's going at, what, 225 million meters per second, and in so-called empty space, it's 300 million. So obviously, the speed of light is not constant. It depends on where it is traveling. And one of the things we had noted when we studied the gravitational redshift is that the speed of light actually increases as you go away from the Earth. And only tiny amount, but it does increase. And so that's why you get longer wavelengths as light goes away. And that has been called by the relativists to such things as time dilation or whatever. And of course, that's kind of silly. Time doesn't dilate because time is motion. Only things can dilate. So yeah, light is going to be different. The speed of sound has changes depending on temperature, pressure, and so on. And so we have not found any constants. It's sort of like pi is not a constant. And that's the way the infinite universe occurs. Pi has an infinite number of characters after it and digits. And what we have is essentially that for everything. Now, light is quite precise as it travels through only ether, which we, empty, so-called empty space. That is true. And the changes are slight. And but nevertheless, we can't expect to be constant.
Now, you did mention stuff.
One thing I also wanted to point out.
Go ahead.
Okay, what I wanted to point it out. Remember, this whole Big Bang mess that we got into is based on Einstein and his idea that what I call untied light theory, and I haven't heard anybody else call it that. But what he essentially is saying is that, even ether or as a particle traveling from point A to point B can do so without losing energy. Now that defies the second law of thermodynamics. Remember what the second law of thermodynamics says. You lose energy through the interaction with the environment. And it's sort of like this. If you're trying to move electricity from New York to San Francisco, what's going to happen? Is it going to be 100% transmittable?
No, absolutely.
Have you ever stood under a transmission tower? What do you hear?
A lot of crackling.
It's buzzing away, right? Yeah, and so that's what happened. And so the misinterpretation of the Hubble law is exactly that. It's essentially saying that light can travel without losing energy, and there's no way that could possibly happen. And that's so in infinite universe theory, we don't have an expanding universe.
Well, you took my question, because that was exactly my follow-up question, but you got to it before. Like minds think the same. So there you go. I was going to wait. That was my
there you go.
Good. Hey, I didn't even have to ask you. In fact, I'm just going to turn it over to you and turn off my mic here. So no, I'm just kidding. No, absolutely. When you were talking about that, I said, "This is what about the redshift? This is like goes against all of that." So basically, what you're saying is that anything that's moving, light or whatever, you can't have. It's not perfectly. You can't. It's going to lose some of its motion. If it's going.
Let me explain that a little bit. and I've emphasized this in the last book. I didn't in previous books, but what we're talking about is waves. Now, to produce a second wave after, say you have water wave and it's moving along, and now it's going to produce a second one. In a perfect world, that second one is identical to the first one, but that's not how a world works. It loses some of the motion. So the second wave is not the same as the first wave. And what we see there is a lengthening in the wavelength, and that's what the redshift is all about. And so this is simple. This is not complicated. That's why I think people should read Infinite Universe Theory. It's easy. It's not that hard.
Yeah.
And there are some difficult parts, of course, because I'm satisfying some of you physicist types, but nevertheless, I'd say half the book is understandable by, most people.
Most people get the Newtonian world. Yeah. Most people get the Newtonian world. Right. So your ether theory and our particle theory are very easy to understand. I put it no math. I mean, all you have to understand is the concepts. Both of those theories have a lot of the things that you described in ether. We just in ours, because we came up with the wave model with just particles, that they're very similar. You don't need to know. You don't have to write down one equation to have to understand or visualize in your mind, because we live in a sort of Newtonian world. That's what we see. And so being able to then say, okay, if it's ether where things are hitting and the wave goes through ether, or whether they're particle waves of particles, whatever it is, you can see it. You don't need to write down complicated equations. All right, let's keep going, because I've got another part here, which, hey, something that I'm going to disagree with you, but you know what's really great about it? It doesn't really matter. It makes no difference to your infinite universe theory. And that is one of the things you talked about was dark matter. And one of the things that if you haven't seen, and this is, I'm telling you the great Dr. Glenn Borchardt to take a look at somebody else's work here, but take a look at my dad's work. When you look at the graph of the speeds of the stars through the galaxy, it mimics the physical makeup of the galaxy as matter. And so if you just take the regular a shadowing effect, and you take the gravitational field, which of course you will totally agree with, which is not uniform through, and it's totally has to do with the geometry of everything around it, that in fact all the speeds can be calculated. There are two papers that, one paper that was out a couple years ago, written by Cameron Wong, and he started applying Newton's equation to rods and crosses, and he found out that he could explain very closely those velocities of those stars. But I think you bring up another point, even though I think there is no dark matter, because you talk about dark energy, and so I'm going to put that in here, and maybe we can focus on that and not really discuss, so you and I get into whether dark matter really exists. But I think a good point that you make here, it says roughly 68% of the universe is dark energy. Dark matter makes up about 27. The rest, everything on Earth, everything ever we all observed, I'm going to try to read this again here. The rest, everything on Earth, everything ever observed with all of our instruments, all normal matter, adds up to less than 5% of the universe. But you talk about this, the dark energy versus the dark matter.
Okay, remember that energy doesn't exist.
Yeah, sure.
Energy does not exist. Energy is a calculation. Now, this calculation was required for the Big Bang, because they had to have something that was doing the banging. And so that's where the energy comes from. That's where you get 2/3 dark energy or whatever, in order to get the kind of expansion that they think happened by using their assumption that of untied light. So there's no such thing. So what you do have then is dark matter. There's no reason that all matter should be luminous.
Right.
That's absurd, because you can't. Much of the universe is not luminous. It only gets luminous after it's been squished together, and like the sun and so on. So I think what you were talking about is kind of neat, is that the galaxy acts as though it was filled with matter. Okay, and I'm in our universal cycle theory Steve and I talked about the fact that smaller and smaller particles would be not seen in the galaxy, and that when you spin something, these smaller particles are pushed to the outside and so on. The large ones essentially are pushed to the center. And anyway, that was, now I've come up with some other thoughts on that, which I call ether deceleration theory. And this explains gravity. And the reason it does is it's a local phenomenon, and essentially says that ether crashes into baryonic matter.
Mm-hmm.
When it does so, it becomes decelerated. That's Newton's second law. Remember, one thing colliding with another. This is something that I have not seen anyone else talk about. And it's obvious. When you study gravitation, it always involves an acceleration. Acceleration by what? Einstein says the gravity is what, a bent space or something. And others talk about attraction, which there is no often have an attraction law. His three laws don't talk about that. And essentially, what you got to do is keep your eye on the ball, and that is what is colliding with what. Remember, that's where we got onto this boat, is matter in motion.
Right.
And okay, so then when these particles collide, what do? They're slower.
Right.
They hang around, and that's why ether is then trained around the Earth, and that is why the Michelson-Morley experiment was not able to detect ether. Why? Because it was entrained.
Right.
They were looking for a fixed ether through which the Earth was moving, and the ether was carried along with the Earth. That's the key.
Right.
And so, anyway, there's more details in that. The ADT theory, ether deceleration theory, is really good because you have increasing density near matter. What is matter? Matter is made out of ether. What else? Like you were saying, ether 1, 2, 3. That's what happens in an infinite universe.
And along with that, I'm going to skip down to another one because I have some notes here, but it has a lot has on the same subject. Location 3867. Instead, LIGO destroyed. Instead, did it find gravitational waves? LIGO, right? Instead, you say no. Instead, because you have some questions in the book now, I remember, right? You said, here's a question, and you say yes or no. And I think one of them was to the fact that LIGO did it detect gravitational waves? And you said no. Instead, LIGO destroyed both gravitational attraction and ether denial as viable theories. Ever since gravitational waves were hypothesized by Einstein, regressives tried to get data proving him right. So tell us a little bit about what you're talking about. It really fits in with this idea of, oh, this the latest thing, LIGO. I'm sure it'll be they already got a Nobel Prize, didn't they?
Yeah, they did. That was one of the fastest ones. And that's at first when these things come out, I'm not quite sure whether they're legitimate. This appears to be legitimate. They have a couple of experiments, and now they're able to locate essentially light traveling at the same speed as their shock wave. The shock wave that they measured, they said in the newspapers anyway, that this was a result of compressing empty space, which doesn't make any sense at all, right? You've got to have ether for that to work. So the ether denialists are going to have a little rough time with that.
Yeah.
And so that's one of the things they do. And the other thing is, it's obviously not an attraction, because we're not that attractive. If these exploding black holes or colliding black holes are producing a collision, it's going off in all directions, and it's not not being attracted by us in any way, shape, or form. So attraction should be done. We shouldn't be talking about gravitational attraction. I'm sure they'll be doing it for another 30 years, but that is totally gone. And also, like I said, gravitational waves, that's not how gravity actually works. Gravity works on a very short term, a short distance, as we explain in the ADT and ether deceleration theory. And it's very similar to your atmosphere, where you have particles banging around, and they push things around, and it's all local. I totally disagree with those who, like Duncan Shaw and so on, who who actually say, like Lesage did, that these particles come from a long distance and so on. And I'm pretty sure that you can say the lack of aberration essentially eliminates that particular possibility. And so that's why I like the local effect. It's just the pressure effect. The pressure of ether is greater further away than near it is to Earth. So
Right,
it is. So
right,
it's sort of the reverse of the atmosphere.
right, right, right. Also, I want to get to part of your book as well. There's so much in it, but I wanted to give you time on it because even though it's different from my father and I's theory, you were talking about. I remember you had mentioned to me that you were hypothesizing that the ether was more like sort of a flying disc, sort of. Right? It was sort of like two hubcaps put together that are really sort of rounded. And there was a reason for that because of the types of waves transmission. I think this is the first time you really talked about this in real detail. Is that true?
Yeah, I think my other books didn't get into that. And for one thing, the vortex model that I use is very similar to what we see throughout the solar system's vortex and the galaxy, the Milky Way galaxy. And everything seems to want to revolve around everything else. And that's how the universe is put together. And so I said, okay, well, let's just take it down a step and have ether particles be that. And that would explain one of the big problems with ether theory is that it has mostly T waves. Now, T waves are transverse waves. They go sideways. And then, of course, there's L waves that go back and forth. And L waves are common in such things as sound in the atmosphere.
Mm-hmm.
Now, the particles that are moving there are nitrogen, molecules, and so on. They're almost round. And so they bang together and they can do L waves back and forth. And the problem is with light, that isn't what happens. They only go sideways. And so I figured that, all right, the ether particle must be like a flying saucer, or like the sombrero galaxy that I give as an example.
Mm-hmm.
And that most of it is not edged. The edge would produce some actual L waves, probably 1% or less, but most all of it will be T waves. And that's why I would come up with that.
Yeah, and that's something that's
yeah. That's the morphology of ether.
Yeah. Now that was something new I saw too. I know also you talked about you also I remember talking with you a number of years back and asking if you had seen Lionel Deneu's work, which was gave us some real insight as to what people call attraction and repulsion, because of course it has to be eventually broken down into matter and motion. And so you also mentioned, Deneu's work in your book. I think that was the first time as well. Is that true?
Yeah. So sometimes you can't always find where his stuff is, but he has a YouTube on it, and of course YouTube is more popular now than ever. And so he has a really good demonstration of the fact that if you have two things moving in counterclockwise, one's counterclockwise, the other is clockwise, you'll get these effects of attraction and repulsion depending on which way they're spinning. And I thought that his demonstration was really good. He uses water, of course, but it would happen. I think the thing that he really is emphasizing, and I put it in the book too, is that the whole idea of charge is not a system property, which is what scientists typically do these days. It's a environmental property. It's a property of the thing and its environment. Without the water, his demonstration would not work. It has to carry some of that water with it in order to get the result he does, where the objects go together and apart, and depending on which way they're rotating. And that's what we're talking about with ether as well. That just you have to have ether for this charge to occur. That's all there's to it. You can't have an empty space. You cannot have an empty space and still have charge. That's my main point.
Yeah, it was interesting because I just talked about
and
that.
And of course,
Go ahead.
Yeah. Well, every mainstream scientist or physicist is going to say, no, you can have empty space. Remember, that was what Einstein
Right,
started with.
right,
And he
right.
even recanted that whole thing in 1920. He said no.
But you know,
He believes there has to be an ether.
it's sort of, well, it's sort of like the Life of Brian, where Life of Brian, he had to give some speeches to save his life from the Romans and try to just start pontificating. Then he had followers, but he didn't want followers. He told them to go away, but it didn't matter. The movement was started, and it went on without him. I think that happened a lot with Einstein himself. I think I had interviewed for my movie.
Yeah.
I had
Happened with
interviewed,
Hubble.
yeah, I had interviewed a guy in my movie, Jack Rosenthal.
Hubble is, yeah.
Yeah, and
Well, Hubble was the same way. He
yeah,
denied that he had ever discovered an expanding universe. And he said, well, there's some strange law that's involved in transmission of light. Well, it wasn't strange. It was a second law, and he should have known better. But he actually talked about expansion in his first paper, which made it very popular because people wanted to hear about that.
yeah, I
But it
think,
was wrong.
yeah,
So,
yeah. Oh, I think people would be surprised to find that a lot of these people who we now consider in mainstream science, people in mainstream science consider to be very, you know, solid in their assumptions, if they had them. Most of them they don't, because if they were to say them, they conflict so much, which already happens. But when we look back at it, that the actual people involved with these things would be as skeptical as we are today, because we do our best to come up with models and make things better. But we know that in the future things are going to be how do you say, improved quite a lot about what we're doing, and that Einstein and all those other people, if you talk to them probably one-on-one, they go, yeah, this stuff is good, but this could all be wrong. So we have this idyllic idea of how all this science works. So I remember talking with you about the book that you did with Steve Pitts. And I had said to you this phrase, and I was just curious. I said, Glenn, you should extract the neo-mechanical part, which is really, I guess, more of infinity. And I wanted to ask you about that, being a student of your work. How do you see it now? Because at the time, there was the cycle theory that was part of it. There was neo-mechanics, and then the infinity part. How do you see the neo-mechanics and infinity today in your infinite universe theory? How would you describe those two? Because I know you've talked about neo-mechanics that's my question. It's my own personal question.
Yeah, right. Well, remember that mechanics is a finite theory, and neo-mechanics is infinite theory. So what it says is that, for example, the number of causes for any effect is infinite. Now with mechanics, with Newton and so on, you'd say, no, it's finite. We can number them, A, B, C, D, or whatever. And it turns out you can't. And the proof of that is that you do an analysis once, and you do it a second time, you never get the same answer.
Mm-hmm.
And the reason is universe is infinite. And that's one of the situations in which neo-mechanics, by the way, I don't have a hyphenation for it.
Okay,
Neos,
sorry.
N-E-O, mechanics. And this is new. Other people have used that term as well. But including infinity is really, really important. And of course, that's in the Infinite Universe Theory book. The only thing is, some people will have to study that in some detail because it's not common if you haven't had any physics. But if you had any physics, it should be a piece of cake, no problem.
Okay, so you're saying that neo-mechanics, that's a good explanation that I wanted to, because when I talked about your work to people, so neo-mechanics is basically in the infinite universe on top of regular mechanics. Is that correct?
Yeah, it's an assumption of infinity in regular mechanics. Yeah, right.
Okay.
Yeah, without infinity, it wouldn't work.
Okay, so we're coming up here on 55 minutes, so that's a good time. What would you like to tell people about this latest book, and what's ahead? I mean, right now it got launched, so you can get it on Kindle format. Is that the only format, or can you buy it also as paperback?
Just Kindle. Paperback is a little bit complicated because this book has a lot of color photos. So I recommend you get it for your iPhone or iPad or for your PC. You can get all the color. And one of the problems is resolution. So I'm still working on it. Someday maybe I'll have a very expensive color book out. But at the moment, it's only on Amazon. And it like I say, try to keep the price down around $10, and
Right.
people should like that. One interesting thing is that a lot of books are post the Big Bang, and I didn't belabor that. I put in a few chapters, tiny chapters, showing why the Big Bang is false. One example, and your audience would love this. If you look at the photos from the Hubble, you'll see that at very great distances, 3 billion light years, there's the same stuff as we have here. The galaxies have black holes in them. They look the same. They're spiral. They are ancient. The universe cannot be 13.8 billion years because it would take almost that long for that light to reach us, so multiplied by 2. And so this is one example. There's a couple others. Things are not all coming apart. Andromeda, for example, is a galaxy that's blue shifted and coming towards us. There's all kinds of things coming towards us. In an infinite universe, actually, you have divergence and convergence. That's what describes it. And so I think that's so. I wasn't going to push the complaints of the Big Bang have been out there for a while. I think what we need is a replacement. Infinite universe theory would be a replacement. It's not going to be multiverse or anything, or a parallel universe or anything, because they're still using expansion interpretation in their work. And I say it's just oxymoronic, because you know what that means? One universe. Don't
Right.
get us all these multi things. Those are all made up. They're dissatisfied. They were like the steady state theory was. Hoyle believed that there still was expansion, but that he was creating one hydrogen, out of nothing or something. And that was still an expansion theory. It was a reformist theory. What we don't want is a reform. We want a total radical change from finite to infinite.
Yeah, that's an understatement. Like I said, it was one of the three things that exploded my mind in my scientific career is your work. I just, I think it's hard for me being a person who sees stuff. I always told everybody I never had my own theory until then my dad came along and gave us a different type of look at a model, and we're just working with it. But I will tell you, I guess it's sort of like a personal journey, because that's what we all have in life, is to be able to be close to people that are changing, the way the flow of science goes at a big scale. And I think your work, you say it, but it's absolutely true. This is a huge paradigm shift, and I had always told you that someone come along and use your infinite theory, universe theory, to make a model. My dad or two of us, right or wrong. But I will tell you, these are the beginnings of that shift, and I really do think that we're at a time where people are going to more and more get this, because there's just so much. I think the reason I had such a tsunami come over me when I read your, all these levels, the ether levels and all those kinds of things, that tsunami hit me, because all the problems of affinity, just they seemed, I couldn't come up with a solution. I didn't know what to do. And then when you came along and said, turtles up, all the way down, and was explaining it with, in this case, an ether model, it wasn't even the ether that blew my mind. It was just the plain old idea. That's infinity. The other thing that I do talk about, if you follow some of my videos, is the way I explain, I am much more comfortable with the idea that there are parallel universes, but they're parallel in the sense they have a place in space. There's a three-dimensional place for it. There's no such thing as two things existing in that same place. And yeah, if you think about the infinite universe, you've got all these little things around you. I remember in the 1960s when I was growing up, I remember somebody smoking some marijuana in some film or something like that. Why I was seeing this or hearing this at 10, I don't know. But people, once guy was Cheech and Chong me, I don't remember, but he says, you know, it's like maybe we're an atom in somebody's chair. And if you were looking at what you're talking about with the infinite universe, you sort of look at it that way. I mean, we have these galaxies flying around. I mean, that's an ether for something else going on. Maybe we're transmitting waves. It's going to be forever. It's going to be a long time. It's going to be that Woody Allen thing where you're going to have to wait a long time. But I mean, I really feel very comfortable with that idea that you have, yeah, there's little universes, but they're not parallel. They're just, there's a place for them. It's just way down, way up. And, you know, I think it just, so many things fell into place. I just want to congratulate you. I always say, like, sort of like, for mankind, whether they know it or not, thank you so much for your work. I know people, the more I talk with people, they come across, when they see it, you can't get out of it again. That's a paradigm shift. A paradigm shift is when you see something like your work, the infinite universe theory, you get it, you understand what it's about, and you can never go back. And that's, you know, applause to you. And, you know, thank you so much for taking the time. And of course,
thank you so much.
Of course, I'm going to be working with you and audience. I think we're going to do it. I think he's going to get on YouTube and start his channel, because I will be watching everything he comes. I don't care. I know this stuff I know this stuff a lot. It's still listening to Glenn talk about it will be just great. The other thing too is I'm going to tell you, Glenn, that my dad's working on his model, which again is a different model, but it's a recording of your work. It's a recording of you talking about what you've done. And in today and age, it's not a documentary that doesn't need to be there. You can talk to the whole world. When you sit down and talk, that goes on for 10 years, 20 years, for a long time, maybe even infinitely. So thank you so much.
There you go.
So thank you so much.
Really great.
So you are going to.
Okay.
Do I have a promise?
Yeah.
Do I have a promise from you that we're going to try to get this the Infinity Guru off and running the channel? Yes. Do I have sort of like you're willing and able, right?
I'm looking forward to it. Yeah, it'll be a lot of work, but hey, I think it's worth it. I think what we're looking for, though, is the average person to understand.
Absolutely.
That's why the book is written with like half of it is really understandable, and we need to do this because it's not going to be done from inside. Yep. Paradigm shifts always occur from the outside.
Absolutely do. Yeah, it's the macrocosm.
That's why we need a lot of people.
I mean, your theory explains why there's paradigm shifts. It's from the macrocosm, from the outside. It's the pushing from the outside. And you know, the good thing is that the mainstream physics is failing today because their systems are so paradoxical that it's not that you have to be really smart to understand them. You can't understand them. It's a joke. They're pulling a fast one on us, because basically what they're saying is, oh, the reason you don't understand that paradox is because you didn't go to our school and learn it. What really there is capitulation. If you're my professor and you're saying, oh, there's paradoxes in relativity or the Big Bang or whatever else it is, what it ends up being is I have to consciously decide that I will accept a very failed system and go along with you. That's what science is today, and it's amazing that the models are going to simplify, and when they do, they should be understandable by everything and everybody. And the infinite universe theory is absolutely understandable by everybody. Thank you so much, Glenn. And like I said to my audience all the time, don't take my word for it. Don't take Glenn's word for it. Don't believe him. Go get his book, read it for yourself, And believe me, if you are a critical thinker, you're not going to be able to go back. Once you read his stuff, you're going to be indoctrinated, and you'll become a student and follower of an amazing shift. Congratulations, and ciao for now.